Let's start. So, refrigerant. We will learn basically the basic details of refrigerant, what is the importance, characteristics, and the properties, and which refrigerants we are using, and basic details. So, what is refrigerant? See, this is our indoor AC in our normal home, normal room. We put these split air conditioners in everywhere nowadays, and this is the outdoor unit, and these units are connected by a pipe. So there's a pipe is connected between this indoor and outdoor unit, and that is called refrigerant pipe, and refrigerant is flowing through this pipe. So a refrigerant is working fluid used in refrigeration, air conditioning, heat pump to transfer the heat. It undergoes phase changes, typically from liquid to vapor and vapor to liquid, to absorb heat from a low temperature environment like in our room to high temperature environment like atmosphere. So if you see the simple diagram, this portion is the heat absorbed from the room, normal our room where we keep our indoor AC, and this is the rejected heat to atmosphere, which is basically our outdoor unit, which we keep outside the room or even the roof. So we can define refrigerant. It is a working substance or a heat carrying medium which during refrigeration cycle absorbs heat from a low temperature system and discard or dissipate or remove the heat to a high temperature system through change of phase of substance such as evaporation or condensation. This is basically the cylinder it looks like where the refrigerant we keep. Like, see, this is a 407C is the name of the refrigerant. You can see this 410A, or you can see R22. These are the refrigerants. It will be name plated like that so that people can understand that which refrigerant it is. Now, properties. Low boiling point. That refrigerant is one of the necessary property that the boiling point should be very low so that it can boil at a very low temperature to keep the heat from the surroundings. If you see, the water boiling temperature is 100 degrees centigrade. However, if you consider any refrigerant like R134A or R410, R22, whatever, their boiling point is very low. For R134A, it is minus 26.3 degrees centigrade. For R410A, it is minus 48.5 degrees centigrade. Now, high critical temperature. This is one of the another important properties that critical temperature should be very high, and it is already high. If you see that diagram, R410 to R133 ZD, whatever, there all the critical temperature is very high. Now, high latent heat of vaporization. So if you see, the latent heat of vaporization is, it is already tabulated. For R410A, it is 214.48 kilojoule per kg, and all other are listed. And high latent heat of vaporization is always necessary for the refrigerant, and the selection of the refrigerant, it is one of the most important criteria. We will see it in the details later on. Now, low freezing point, that the refrigerant which we are using for HVAC system or air conditioning or refrigeration or heat pump, it should have a low freezing point. Otherwise, the refrigerant will be freezed, which will not be able to flow. For freezing point, if you see R744, it is minus 56.55 degrees centigrade. R1348 is minus 96.6 degrees centigrade. R410A, it is not there, but it is minus 155 degree centigrade. It's like that only, so it is very less. Now if you see that low specific heat of liquid, here low viscosity, so it will flow without much friction. If you see the viscosity, all the data is tabulated here for information. You don't need to keep in mind, just for information. High thermal conductivity, it is essential for heat transfer, and non-toxic. That is the for environment point of view, it is non-negotiable. Now non-corrosive, so this refrigerant should be non-corrosive, otherwise it will react with the surface of the pipe or the materials or the equipment, and it will corrode, which is not uh, accepted in the system. Non-flammable, yes, this is also one of the important property. Then non-explosive and environment friendly. Yes, currently all the refrigerant which are in under progress or under consideration, it is trying to consider as possible as it will be environment friendly. Chemically stable, so refrigerant will be based on the stability, availability, it should be available, and low cost. This is also in case of we have to keep in mind sometimes, but whatever it is, we have to select the refrigerant based on all other criteria. Cost is later on will come. Low ODP, that is the ozone depletion potential. There are many refrigerants earlier used which deplete the ozone, especially for whenever the AC equipment is under maintenance or any leakage. This refrigerant gas will go to the atmosphere and it will be going to above the earth surface, and it will just break this ozone layer, which is very difficult because UV or other rays which is harmful for the earth, for the environment, will enter into and it will create problem. So this is definitely it's one of the most important criteria for selection the refrigerant. If you see the ODP table for R11, that is CFC 11, is ODP 1, CFC 12 it is 1, and this HCFC 22 it is 0.055. So these are gradually it is reducing, and nowadays the refrigerant which is used is a HFO type, which is having ODP 0, and it is highly recommended to consider this HFO type with a 0 ODP. If you see a table here, all the refrigerant with respect to ODP is listed. One more important criteria is that global warming potential, or GWP. This is basically the refrigerant which is increasing the temperature of the earth atmosphere, so it contribute to the global warming. So that's why all the refrigerant is classified, or it will be considered as this global warming potential rate, what is the value, and lower global warming potential is always recommended, and it is non-negotiable. If you see the GWP list, it is tabulated here. Here in the list, if you see R134AYF, R1234ZE, these are the GWP, and R404 or R410A, R22 is having high GWP. Type of refrigerant. It is chlorofluorocarbons or CFCs, which was used earlier. Hydrochlorofluorocarbons, HCFCs. Hydrofluorocarbons, HFCs, and hydrofluoroocarbons, olefins, HFOs. These are the main type of refrigerants, and currently we are in HFOs zone, and many companies, many industry, they are using HFOs nowadays, which has a very low GWP and zero ODP. If you see CFCs R11, R12, R113, R114, HCFCs like R22, R123, R124, R142B, HFCs like R134A, R410A, R404A, R407C, and HFOs, if you see that currently R1234YF, R1234ZEE, R44A, R1234YZ. These are commonly started to use for protecting our environment as well as to get the maximum effect. There are many other refrigerants as well. However, we have listed based on the current use in various industries. So CFCs, HCFCs, HFCs, and HFOs. If you see CFC, high ODP and high GWP, HCFCs, low ODP and high GWP, HFCs, zero ODP and high GWP, and HFO, zero ODP and very low GWP. So the transformation is from CFCs to HCFCs to HFCs to HFOs. Now we are in HFO stage, and maybe in future the some refrigerant will come which will have more definitely better than that also. So research is going on continuously, and also there are a lot of machines are already with CFCs, HCFCs. So there are many criterias which year it will be obsoleted like this. So lot of protocols are, lot of things are going on for the refrigerant to protect our environment. Refrigerant classifications. Based on ASRE 34, the refrigerant is classified as per this table based on the flammability as well as the toxicity. If you see this table, this is one of the most important table where there are a lot of questions comes in the competitive exams. So if we know these things, it will be better definitely. So this is basically the increasing toxicity. So toxicity level is in the X directions, and the flammability level is on the Y directions. So increasing toxicity means it is going to A to B. If it is A, it is lower toxicity. If it is B, it is higher toxicity. And on the simultaneously, if you see about the flammability, so 1, that's A1 or B1. 1 means no flame propagations. If you see about 2, like it may be A2 or B2, it is flammable. And 3, it may be A3 or B3, 3 means higher flammable. There is one more, that is A2L or B2L, it is lower flammability. So A means lower toxicity and B means higher toxicity. Now 1 means no flame propagation, 2 means flame propagation, flammable, and 3 means it's higher flammable. Other refrigerants like inorganic refrigerants and based on use in the refrigeration cycle. So inorganic means like ammonia R717, or air like R729, carbon dioxide R744, and sulfur dioxide R764. Based on the use, it is primary refrigerant or secondary refrigerant. Primary refrigerant means the main refrigerant which is used in the refrigeration cycle, like R134A, R410A, R407C, which we have discussed in our previous slide. And the secondary refrigerant, it's like water or brine, that means water plus salt or glycol. These are the refrigerant which is used for transferring heat from the primary refrigerant. So this is called secondary refrigerant. Common refrigerants in our industry like R134A, R410A, R407C, R1234YF or JDE. These are the commonly used refrigerants in our industries. Designation of refrigerants. We see the refrigerant, it's written as CM, HN, CLQ, where if you see this, C is carbon atoms, H for hydrogen atoms, F indicates fluorine atoms, and chlorine, Cl, indicates the chlorine atoms. Now for the CmHnFpCl, it is written for the refrigeration format, in the refrigerant format, Rm-1, N plus 1 and P, where if you see R means the refrigerant, M equals to number of carbon atoms, N equal to number of hydrogen atom, and P represents number of fluorine atoms. And there is an equations. It is written as N plus P plus Q equal to 2M plus 2. So this is the equation we have to keep in mind. And these things we have keep it here because there are many times question comes for competitive exams or the certifications for these things. So if we know this, it is better. So we need to keep in mind N plus P plus Q equal to 2M plus 2. Let us, for example, CHClF2. If we compare our format CmHnClPFQ, we can write from these things that CHClF, here C1, H1, Cl1 and F2. Simply we are comparing with CHClF2. Now CmHnClPFQ, we can compare and we can write M equals to 1, N equal to 1, P equal to 2, and from our format R M minus 1, N plus 1, P, we can write R, putting M, N and P value, R 1 minus 1, 1 plus 1 and 2. So it will be R022 or R22. Now R22 can be here, can explain that this 0 is number of carbon atoms, M minus 1. This is 2. It means that number of hydrogen atom plus 1 and N plus 1. And this one is number of fluorine atom. So it will be P. So how to detect refrigerant leaks? There are visual, then auditory inspection, olfactory. All these things it can be detect the refrigerant leaks.
Excuse me.
Gas.
Sir, in last slide,
Yes.
the P value is 1 now, sir.
Sorry.
P value is 1, right, sir? Cl 1.
P value is
1, right?
1. Just a second. P chlorine. Where you are telling? Okay. P is okay. It will be Q. I hope. I will change these things.
Okay.
Or here it will be altered actually. Okay. So it will be 2 will be coming. For if you see F2, it will be coming like that only. So it will be altered. We'll change the slide.
Here
I'll
you
update.
consider F is also pure, sir. It's
Yeah,
2 and P is equal to 2 now. Yes.
yeah, yes, 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 yeah. Yes, so then gas detection agents and UV detection, electronic leak detectors. There are many places for if you see about offshores where that or the cold region, if you see there are some that refrigerant there is a chance of freezing. There are many refrigerants are chances of freezing. So that time this is and it can be flammable also. Many refrigerants it can be flammable as well. So in case of flammable means up to certain level it will be flammable. Means their temperature, flammability temperature is high. But in case of any chances, if there is a leakage, then there will be an explosion kind of things. So that particular cases, leak detection is very very mandatory. So that things are require many sensors or kind of systems needs to be, or some drains should be connected with a sensor so that that flammable refrigerant can be drained out to the safe area or to the dedicated place where there will not be any chances for explosion or anything. Now, if you see, there's a lots of discussions, lot of protocols. This is a practice for refrigerant, so that continuous evaluations since long it is happening. That's 1987, some Montreal Protocol. Their CFCs and all things are required. So they basically they discussed how to evolve the refrigerants to make our environment friendly and to give the least impact on the our environment. Then in 1997 Kyoto Protocol, here also HCFCs has considered and discussion about to reduce the use of all uh, chlorofluorocarbons and all these things, and the Paris Agreement 2015. So these all HFOs are introduced and it is continuously growing, and still the discussion is going on so that we will have the HVAC systems without much impact in on our environment. Basically, if you see, there are the timeline, and it is a continuous process. So that these evaluations of the refrigerant is still going on, and the limitations up to where this all refrigerants which is already installed in the equipment will work up to how much time. So a lot of discussion is going on continuously, and um, it is a continuous process which I hope will be sorted out in future also, and we will get some best in refrigerant which will have maybe will not have any impact on our environment. So safety data sheets. There's one more simple things I will tell, that what is SDS. Earlier it was called as MSDS, Material Safety Data Sheet. Now it is called SDS, or it is Safety Data Sheet. So this is also simple questions. It comes in the competitive exams. So a document that lists information relating to occupational safety and health for the use of various substances and products. So we will see the standard safety data sheet for the refrigerants. If you see, the name of the refrigerant will be indicated along with certifications, and it's a this address and all these emergency call some things. This is a normal things. It should be in the safety data sheet. Its classifications is potential health hazards, all these uh, reactions with eye, skin, inhalation, ingestion, all these things at least has to be indicated in the safety data sheets first, and measures, all these details has to be there so that the people or this or the people will know about the consequences of the refrigerant during handling or installation or the maintenance. Firefighting measures has to be indicated, its flash point, all the method, auto ignition, temperature, all these things should be there, and any explosion things are there or not, that has to be there, or what are the measures, accidental release measures has to be there, handling and storage during the storage and how to handle all the details has to be there in the safety data sheet, and the personal protective equipment related to the refrigerant will be captured. Physical and chemical properties, you see the boiling point, freezing point, vapor pressure, all these details is captured in the data sheet of the this SDS. Stability and reactivity, then this information, toxicity level. So these all are part of basic refrigerants. Now we will try to understand the tonnage of refrigerants. So tonnage of refrigeration, that is the very basic term in our HVAC system, and we will learn here basically introduction, definitions, its calculations, value, units, unit conversion, use. So this is very basic, but I think it is better to have a basic knowledge how the tonnage is calculated or what is actually the tonnage mean. So I know that you all know these things, but I have captured it here just for brush up our basic knowledge. So what is tier? If you see the chiller, or if you see the package AC or even split AC, any air conditioning equipment, you can see that it is many times it is indicated some capacity in tonnage TR. So we need to understand the tier, and many times it is kilowatt in other units as well. So we have to understand what is the basic term, that is the tier. So in our home, we see the split AC, normal split air conditioners. We keep nowadays the temperature is elevating. So many places, even the village, also the split air conditioner I have seen. So there's a one unit in the inside and another unit is outside, and the connection by refrigerant pipe. So indoor and the outdoor unit. Now, if you see the nameplate, it looks like this. See here, and this is any AC. You can see there will be a nameplate, and you see there's a cooling or heating capacity. It says 5303 watt. So this is basically we are equivalent to tonnage. It is in different unit. So we try to understand the unit for air conditioning loads or the cooling capacity, heating capacity, which unit we basically use. We miss, and we will try to understand how to derive. So if you see the indoor unit, you can see its nameplate is here, and many it depends definitely on the manufacturer, but for typically I have written it here. In the outdoor unit, you can see the nameplate. Here there is one nameplate. You see minimum capacity, that is 254 ton. So tier. So we should know that what tier means. Let's define what is tier. The cooling capacity of a refrigeration system, that is the rate of heat removal from the refrigerated space, is often expressed by the term ton of refrigeration. It can be written as ton of refrigeration, tonnage, or ton, or tier. So definition of tier. Say this is a ice of 1 ton. 1 ton means 2000 lv or 2000 pound. From this diagram we can say that 1 ton of refrigerant is equal to the rate of heat energy needed to melt 1 ton, that is 2000 lb, which is equal to 907.184 kg of pure ice. 1 ton of refrigeration is equal to the rate of heat energy required to melt this 1 ton of ice at 0 degree centigrade temperature in 24 hours. So if we see this 1 ton of ice, it has to melt at 0 degree centigrade temperature in 24 hours. Then this we say that it is 1 ton of refrigeration or 1 tier. The capacity of a refrigeration system that can freeze, we can define in other ways as well. The capacity of a refrigeration system that can freeze 1 ton of pure liquid water at 0 degree centigrade temperature in 24 hours. So TR can be defined in both either ways. So I hope it is clear. And let the value refrigeration effect 1 ton equals to 1 ton into latent heat of fusion for melting, that is BTU per pound, and time duration, that is 24 hour, that is based on the definition of TR. So 1 ton we have written, it is basically 2000 lb. We have written into lb or pound. So 2000 into latent heat of fusion for melting, it is 144 BTU per pound and 24 hours. If we write, it comes 12,000 BTU. So 12,000 BTU. So 1 ton equal to 12,000 BTU per hour, we can say. And we need to keep in mind because it is required many times in our designing. Now if you see in the other unit, refrigeration effect 1 tonnage equals to 1 ton into latent heat of fusion for melting, that is kilojoule per kg by 24 hour. So 1 ton equals to 907.184 kg and latent heat of fusion equals to 335 kilojoule per kg and by 24. So it is 12,662.78 kilojoule per hour. And if we change into kilojoule per second, we are just dividing 3600, so it will be 3.516 kilowatt. So 1 ton equals to 3.516 kilowatt, and this equation we have to keep in mind. Basically, if we know the process how to derive, it will be keep in mind automatically. Now here 907.184 kg is 1 ton, but it is not 1000 kg because 1 ton of mass of pure ice is little less. It is 907.184 kg. That's why we are using 907.184 kg instead of 1000 kg. Now 1 tonnage equivalent to BTU per hour, that is 12,000 BTU per hour, BTU per minute 1200 BTU per minute, kilojoule per hour, that is 12,662.78 kilojoule per hour, kilowatt, that is 3.516 kilowatt, and watt, that is 3516 watt. So you don't need to remember everything, but we need to remember at least 1 ton is equal to 12,000 BTU and 1 ton is equal to 3.516 kilowatt. That these two things we need to keep in mind. So these are the units, and if you see the this nameplate, you see this is 5303 watt. Sometime you see this is in BTU hour, here it is kilowatt, and sometime you see this is tonnage. So we need to keep the units and the conversion in our mind So it will be very helpful in our calculation or in our estimation or in our designing of HVAC system. Now we will move to vapor compression cycle, refrigeration cycle. So vapor compression system. We will learn basically the introduction, concept, components, example, principle of operations, how does VCR works, explanation, diagram, actual process, applications, and many more. So basically the refrigeration cycle is a thermodynamic cycle that generates refrigerating effects with the use of couple of equipment. We have learned the thermodynamic cycle, so it is simply a thermodynamic cycle which generates refrigerating effects. This process is basically a thermodynamic process where the working fluid absorbs the heat from the surrounding at a low temperature and reject the heat to the atmosphere at a higher temperature. So vapor compression cycle, here is the main thing is that compression. If we think about the compression, you see this is the compression of any substance. So here in our HVAC system, you see there is a component is using and compressing that substance, and it is basically the compressor. And due to this compression, we see this cycle as vapor compression cycle. And compressor is the heart of HVAC system. Now, where from this refrigeration cycle came? Let's try to understand and go back a little. This is a Rankine cycle. The Rankine cycle system consists of a pump, boiler, turbine, and condenser. You see the boiler, it added heat and the water formed as a steam. Then it goes to the turbine. Here expansion happens. We got some work output, and then it goes to the condenser for heat rejection. And here's the pump where we put our work, and the cycle goes going on. So this is the cycle basically. In the work out here from the turbine and work in the pump, and the cycle continues. For refrigeration cycle, it is basically a reversed Rankine cycle. So refrigeration cycle works based on reverse Rankine cycle. You see the basic cycle. This is the compressor where we need to work. Here compression happens. In our Rankine cycle, it was vice versa. And this is the expansion. So let's get into the basics.
Let's consider a hot body and it is kept at 50 degree centigrade temperature, and there is a cold body and it is set as 23 degree centigrade temperature. Now what do you think? Heat will flow from hot body to cold body or cold body to hot body? Definitely it will go from hot body to cold body or higher temperature to lower temperature. So heat flow happens from hot body to cold body. And this is a simple heat transfer philosophy which we have learned in our basics. Now consider outside is very hot and it is about 50 degrees centigrade and your room is 24 degrees centigrade. So what will happen? Gradually the heat will flow from outside to inside of the room and the room temperature will increase. Say it is 35 degrees centigrade and over the time it will be more. Now 35 degrees centigrade, is it comfortable to us? No, it is not comfortable to us. So what we have to do? We have to remove the heat from the room. So how to do it? So this is the cold body and this is the hot body, and we have to transfer the heat from cold body to hot body. So what to do? We have to work. We have to do externally. So external work should be done. And that is why the concept of refrigeration cycle comes into picture. Let's consider a
Now the component, let's try to understand the different components of our refrigeration cycle. In our room, we see these split air conditioners, and the air is coming from this unit, and there will be outdoor unit that is mounted on the outside, and it is connected with a refrigerant pipe. So refrigeration cycle or refrigeration system, for basic clarifications, for we are taking example for our home or room air conditioners. One unit is kept in our room, another one is kept in the outside. Now there are main four components which are in indoor unit as well as in the outdoor unit. We will differentiate. So evaporator, compressor, condenser, and expansion valve. So refrigeration cycle is used to cool and heat or comfort design as per process temperature requirements. So it basically based on reversed Rankine cycle, and heat flows from low temperature to high temperature. Let's try to understand the components. First, we will learn in our room AC. This is indoor unit and this is outdoor unit. If you see the isometric, this is basically our indoor and this is basically our outdoor unit. And the components, this is the evaporator coil which is kept in the indoor, and this is compressor. If you see the outdoor unit, inside you see there's a compressor, and this is condenser. This is a coil, it is wrapped just around this unit, and there's the expansion valve, and the expansion valve can be in the indoor or can be in the outdoor, but for normal split air conditioner it is normally it is in the outdoor unit. And this is the refrigerant pipes, and here's the panel.
refrigeration cycle. It has four basic parts: evaporator, compressor, condenser, and expansion valve. It has also few auxiliaries like dryer, receiver, and different instruments. However, we will discuss here the main parts of the refrigeration cycle to clear the basic concept, mainly the main parts of the refrigeration cycle. So these are the main units and all are connected by pipe that is called refrigerant pipe. Normally it is made of copper.
So we will see the first evaporator. Let's see the diagram first. So evaporator, this is the compressor, condenser, and expansion valve. Let's try to understand evaporator.
This is evaporator. In the evaporator, as the name suggests, evaporation happens. See, this is basically a coil for heat transfer. Evaporator. Before learning the evaporator, let's learn how does cooling happens. To understand, let us take one example. This is a spirit. The spirit has a special property of evaporation. At normal pressure and temperature, it start evaporation. Now if you take some drop of spirit on your palm, after a couple of seconds, you will see your palm gets cold. Now how does it happen? Let's try to understand. The spirit has a normal properties of evaporation. Now what do you think? Where from it gets the latent heat of vaporization? It takes the heat from your palm and gradually the palm losing heat. Losing heat means the temperature will be down and palm gets cold. Let's try to understand these things in a simple diagram. This is the palm and this is the spirit. Here evaporation happens. Now this is the contact surface where from the spirit takes the heat for evaporation. So the palm loses heat and gets cold. Now if we consider this portion instead of palm air, and here it is instead of spirit it is refrigerant. Let's see what happens. Refrigerant has a properties like spirit. Normal pressure and temperature, it start evaporation, and latent heat of vaporization it takes from the air. So air loses heat and gets cold. So this is the pipe. So this is the refrigerant pipe. Normally it is made of copper. Refrigerant is passing through this pipe and heat transfer happens. Let's try to understand how heat transfer happens through the refrigerant pipe. This is the liquid refrigerant, and outside refrigerant pipe is hot air, and refrigerant takes heat from the hot air and refrigerant transfer into vapor, and by losing heat air becomes cold. Let's see the transformation of refrigerant and air. So here cold refrigerant changed into hot refrigerant and hot air changed into cold air by losing heat to refrigerant, and this thing happens in evaporator. So basically a heat exchange happens between refrigerant and air in the evaporator. Let's see the evaporator at a glance to clear the basic concept. So this is basically a cooling coil made of copper, and it is like a coil shape to increase the surface area so the more heat transfer can happen. And you see this is the fin. Fin is provided to increase the surface area. Look at the fin from the closer look. Normally it is made of copper and sometimes it can be made of aluminium fin as well. Let's see how does it work. So this is the evaporator coil. Cold refrigerant enters in the evaporator coil and it takes the heat from the surroundings air and it becomes heated and forms liquid plus vapor. Look at this portion. Here liquid refrigerant change into liquid plus vapor and temperature is increased. And after that it takes more heat and finally it becomes refrigerant vapor, and by taking heat it becomes saturated vapor, and again taking heat it becomes slightly over superheated vapor, and it leaves from the evaporator coil. So in the refrigeration cycle we have learned the basic concept about the evaporator.
So in summary, we see about the evaporator. In the evaporator, the refrigerant changes its phase from liquid to vapor at normal pressure and temperature. To change this phase, the refrigerant needs heat, that is the latent heat of vaporization. This heat comes from adjacent medium, air or liquid. We have explained here with air, but it can be with water as well, based on the system. And medium loses heat, and the medium is cold. That is, the air loses heat and air is becoming cold. Now let's try to understand the second component, that is the compressor.
We will learn the compressor. So this is an example of a typical compressor in a refrigeration cycle. So there are different parts of a compressor. Normally reciprocating or scroll or screw compressor is used. It compresses the refrigerant vapor and increase the pressure and temperature. We will make a detailed video for the compressor. Since the vapor is compressed here, this cycle is called vapor compression cycle. So what is the main function of the compressor in refrigeration cycle? Main functions are circulation of refrigerant, increase vaporization in evaporator, and help to heat rejection. Let us try to understand. So this is the impeller of the compressor and it is connected to a motor. When motor runs, impeller will also rotate. And the rotation of compressor impeller creates a low pressure here. And low pressure means definitely it will take the refrigerant vapor from the evaporator. So this refrigerant is low pressure and slightly moderate temperature. So low pressure and slightly moderate temperature refrigerant enters into the compressor, and after the compression refrigerant vapor change into high pressure and high temperature. So basically it creates a pressure differential at inlet low pressure and outlet high pressure. So this pressure differential helps to flow the refrigerant inside the refrigeration cycle. So this is the compressor and this is the evaporator and here is the compressor inlet. Now the evaporator and compressor connected by a refrigerant pipe and refrigerant vapor circulates from the evaporator to compressor. Since compressor sucks the refrigerant vapor, there will be a low pressure within this evaporator and it helps to increase the evaporation process in the evaporator. So it takes the refrigerant vapor from the evaporator. Now let us consider a hot body at 60 degrees centigrade temperature and another hot body as 100 degrees centigrade temperature. And one cold body is 45 degrees centigrade and here also one cold body is at 45 degrees centigrade. Now what do you think? Where heat will transfer fast? In the first one or the second one? Definitely in the second one as the temperature differential is more. 100 degrees centigrade to 45 degrees centigrade. It is same as the water flow from high head to low head. And this is the evaporator outlet. The temperature is less. Now we have to remove the heat to the atmosphere. So here comes compressor. It increases the temperature and pressure of the refrigerant. Basically, it increases the temperature differential and helps to remove the heat. Compressor will not remove the heat, but it will help to remove the heat. We will learn the compressor.
Now compressor at a stretch, we can see due to the rotation of the compressor, a low pressure is created at the suction side. Low pressure helps the vapor to get into the compressor. Here this is not the water vapor, this is the refrigerant vapor. It also helps to have a low pressure inside the evaporator. Since it is taking the refrigerant, so low pressure will be created in the evaporator. And continuous recirculation is maintained by the compressor. So compressor compresses the vapor. In the compressor, the refrigerant vapor pressure and the temperature is increased and a continuous pressure and temperature difference between the evaporator and compressor maintained. This difference increases the speed of phase change from liquid to vapor and helps the refrigeration process faster. So this is a simple diagram for the compressor. One is for low pressure created, two is the maintained low pressure, and three indicates continuous flow. Let's try to understand the next component, that is the condenser.
In this refrigeration cycle, the third part is condenser. Let's learn about the condenser basics. So this is the condenser. It's basically a heat exchanger coil. So look at this. This is coil normally made of copper or sometimes aluminium. This is fins normally made of aluminium or copper, and this is the fan which circulates the air through this cooling coil. So in the condenser, it takes the fresh air, that is cold air, and hot refrigerant comes into this coil. Since the airflow happens through this coil, there will be heat exchange between this refrigerant and the air. Air becomes hot and refrigerant becomes cold. Compressor provide high pressure superheated vapor and it goes to the condenser. So we have to remove the heat. Let's see how does it work. This is basically a heat exchanger coil. High pressure superheated vapor entered into the condenser coil, and due to the airflow through this coil, its temperature is gradually reduced. So the reduction of the temperature makes the superheated refrigerant vapor into saturated vapor. Further reduction of the heat change into vapor to liquid. See, this is the liquid, however it has small amount of vapor as well. And at the outlet of the condenser coil, high pressure refrigerant liquid comes out from this condenser coil. When refrigerant vapor changed into liquid, its volume will be little bit less and the process of condensation will be faster. In this
So for the condenser, at a stretch, superheated refrigerant vapor is released from the compressor. Heat content from the refrigerant vapor is reduced and becomes saturated vapor. Further reduction of heat content from the saturated vapor changes its phase from vapor to liquid. In this phase change, a slight low pressure or vacuum is created in the condenser, which helps the condensation process faster. The condenser is designed considering more surface area with fins arrangement which increases capacity. There are condenser fans to reject the heat from the refrigerant to the atmosphere. Now try to understand expansion valve, the next main component.
let's talk about the fourth part of the refrigeration cycle, that is expansion valve. High pressure refrigerant liquid comes out from the condenser coil. It has some amount of vapor as well. So we have to change this vapor into liquid. Here comes expansion valve. This is the expansion valve. It mainly helps to control the refrigerant flow, and as the name suggests, expansion happens and help to change the vapor into liquid. Let us try to understand how does it work. So this is the expansion valve and this is the inlet where high pressure, medium temperature, saturated liquid enters, and this is the outlet where low pressure, low temperature liquid exit. This is a valve which sends the condition of the vapor and it is touched at the outlet of the evaporator coil. This is the coil. Basically, an independent refrigerant circuit is there within this section to measure the condition of the refrigerant vapor at the outlet of the evaporator. And it can create pressure based on the vapor condition. So here is one diaphragm. Look at this. It looks like this. When the independent circuit refrigerant give pressure, the diaphragm will be bent and the diaphragm is connected with a spindle and there is one orifice and at the below section you see there is one stopper. If diaphragm gives a pressure, then spindle goes down and this orifice will be open and here is the refrigerant will flow. So expansion will happen here as well as it controls the flow of the refrigerant. Let
So this is the expansion valve, the diagram for understanding. The main function of the expansion valve is to suddenly reduce the pressure and temperature of the refrigerant and convert it into chilled liquid or the liquid refrigerant. It maintains constant pressure and temperature. It controls the flow of refrigerant from the condenser to the evaporator. This expansion valve reduces the high pressure liquid line to low pressure in the evaporator.
Let us try to understand the refrigeration cycle and its working process. In the evaporator, air is passed through the evaporator and hot air changed into cold air. And refrigerant takes the latent heat of vaporization and becomes low pressure superheated vapor, and it enters into the compressor, and here compression happens and we get high pressure and high temperature superheated vapor, and after the compressor high pressure superheated vapor enters into the condenser. Here heat exchange happens, cold air becomes hot air and refrigerant vapor release the heat, and refrigerant becomes high pressure moderate temperature liquid. It has liquid plus vapor conditions, and after that it enters into the expansion valve. An expansion happens and we get low pressure low temperature liquid at the outlet of the expansion valve. The valve of the expansion valve is touched to the outlet of the evaporator and control the condition of the refrigerant and flow. So we have got a basic idea about the refrigeration cycle. So here we are getting cold air with the help of the evaporator. Look at this at our home. We see our indoor unit and evaporator coil is here, and we get cooling effect or the refrigerating effect. So we can define refrigeration cycle. The refrigeration cycle is a thermodynamic cycle to generate refrigerating effect with the use of an evaporator, compressor, condenser and expansion valve. I hope the basic is clear. Thank you so much.
Now this definition is applicable for the vapor compression, and there is another cycle, vapor absorption cycle also, that we will learn later on. So chiller, we'll see the refrigeration cycle for the chiller as well. So how chiller looks like, let's see. This is a chiller. I know everybody knows this, but still I keep it in our slide. And this is also chiller. It's a different type of chillers. So for water chillers, let's see a simple diagram. This is the chiller, and this portion, this is evaporator. Here it is cell and tube type. We'll learn later on. This is compressor. Here two compressor is used. This is condenser, and here is the expansion valve. This is the cyclic diagram of the refrigeration cycle, which I learned it in I remember 2008 when I started my career. I have got this. I keep this slides, these visuals with me, and I just use it here. So here you see the evaporator, then it is going to compressor, then condenser, and then expansion valve, and from the expansion valve it is going to evaporator. In the evaporator you see the evaporation happens and the liquid refrigerant becomes vapor. This vapor goes to the compressor, and the compressor, it is pressure and temperature increase, so it symbolizes as the red one. This is the superheated that high temperature and high pressure vapor, and it is going to the condenser, and you see the condenser, it is condensed and we are getting liquid, and small amount of vapor will be present. And then expansion valve, here expansion happens, and whatever the vapor is there, due to the expansion it will change into liquid and it goes to the evaporator, and this cycle continues for going on and on. And there is two circuit, you see that chill water and cooling tower. These are basically used for heat transfer. From the evaporator we take chilled water, and to cool the condenser we use cooling tower. These things we will learn later on. Now we understand this is the evaporator, then going to compressor, condenser and expansion valve. And for evaporator to compressor, you see low pressure and low temperature. Then compressor to condenser, high pressure, high temperature. From condenser to expansion valve, it is high pressure but low temperature because heat is rejected already. And then for expansion valve to evaporator, it is low pressure and low temperature liquid so that it will be ready for evaporation once again in the evaporator. If you draw a line between these two components, we see this above portion is high pressure zone. You see the entire circuit is high pressure zone. And the bottom portion of this line, it is low pressure zone like evaporator and all this circuit. And from evaporator to compressor, it is vapor. From compressor to condenser, it is also vapor, but it is high pressure and temperature vapor. And then condenser to expansion valve, mainly liquid but slight vapor. And from expansion valve to evaporator, it is liquid. So there are many auxiliary equipment also in the refrigeration circuit that we are going to learn here. Just for basic understanding, this is accumulator. See, it accumulator prevents liquid refrigerant from entering the compressor and protecting it from the damage found in the system where refrigerant flow may be inconsistent. So it is basically kept in the liquid vapor line. You see this is between evaporator and compressor. And in case if liquid refrigerant enters in the compressor will be damaged. So that's why it is not allowable to enter any liquid refrigerant in the compressor. And this accumulator is must for all type of in this refrigeration system, especially for compressor driven, that is VCR. And then there will be filter dryer. Filter dryer is kept before compressor and before expansion valve. It removes moisture and contaminants from the refrigerant to prevent system blockage and corrosion. It is function as simple filter. And installed in the liquid line, that is between evaporator and this is between condenser or expansion valve, that is liquid line, or the compressor suction line between evaporator or compressor. Then this is receiver, stores excess refrigerant in systems with variable cooling demands. So this is also an important part, that is the auxiliary part definitely. And then there will be hot gas bypass line, and this is the hot gas bypass valve to prevent the evaporator pressure from dropping too low under low load conditions. For example, if you are in a conference room and it is very low load, then what will happen? The system will stop, or there will be a short cycling, compressor will on and off. So that time if you put the hot gas bypass, it will basically give a small part of the vapor to the evaporator for a load understanding. That evaporator will think or will understand that there is some load, so the system will not switch off or the short cycling will not happen. So this is basically the hot gas bypass valve. Then solenoid valve used to control refrigerant flow automatically in the refrigeration system. And then sight glass, a transparent section in the liquid line that helps to check refrigerant levels and detect moisture contamination. It can be given based on the requirements where these uh, detections are required. And then shut-off valve isolates the compressor during servicing. This is for the vapor line that is between evaporator and compressor. This shut-off valve is kept before compressor and it isolates the compressor during servicing and prevents refrigerant backflow into the evaporator. So no way there will be any backflow from compressor to evaporator. And for the this one, that is the after compressor or before condenser, this sort of valve helps to isolate the high pressure side of the system and prevents refrigerant from flowing back into the compressor during shutdown. So it will also prevent the backflow. And there's one more thing is that evaporator pressure regulator. This is one of the most important thing, auxiliary thing for the control and monitor control. Let's try to understand the evaporator pressure regulator. Maintains minimum evaporator pressure, prevents coil freezing, ensures efficient refrigerant evaporation, and improves multi-evaporator system operations. Now, maintain minimum evaporator means prevent pressure from dropping below the desired level, ensuring stable temperature control. Keep the evaporator above freezing temperature in low load conditions, and for efficient evaporation allows the refrigerant to boil at a controlled pressure, optimizing system performance. And this one, in systems with multiple evaporators, it ensures each operates at its intended pressure. Now if you see this diagram, it looks a little complex but it's very simple. This is basically our evaporator, this is compressor, this is condenser, and this is expansion valve. Now here is the pressure regulator, evaporator pressure regulator, which we have discussed, and this is the suction accumulator. And then you see uh, this is the dryer. Here the dryer, the suction line filter dryer, and here also one dryer, filter dryer. It is before the expansion valve. And there will be oil separator, so that the oil will be separated, because the compressor will have a oil arrangement, oil tank, oil pump, all these things will be there. So there will be some oil, so oil will be separated, and there will be this is the liquid line solenoid valve, and these are the startup valve for the compressor. And here also you see there's a hot gas bypass, which we have discussed, and this is also solenoid valve, and this is a valve which will sense the evaporator conditions. So this is basically the simple diagram of refrigeration system. Now if you see that our diagram in pH or TS, let's see, this is our TS diagram, the temperature entropy diagram, and red one is the high pressure line and blue one is the low pressure line. This is basically the constant pressure line. So this is high pressure line and this is low pressure line. So any line will be like this, and this is basically constant pressure line. So from this diagram, let's try to just brush up our basic. Here this is the saturation line, this portion is saturated liquid line, and this portion is saturated vapor line, and this is the critical point. So this saturated vapor line, this all above outside this saturated vapor line, it will be superheated steam region, and behind this it will be liquid plus vapor mixture. This one is liquid plus vapor mixture, and this is saturated liquid line, and outside this saturated liquid line it will be subcooled, and here is the liquid plus vapor mixture. So in a simple way, this portion is liquid, this is the liquid, this is vapor, and this is vapor plus liquid mixture in our TS diagram. So in the refrigeration cycle, if we take evaporator, compressor, condenser and expansion valve, our diagram will be like this. So this is basically the T, that is temperature, and this is S, entropy. So this is constant pressure line, here is the pressure line. Now from 4 to 1, this is evaporator is placed. So this is basically this process 4 to 1. Here it's a 4 to 1. Here the evaporation happens, and then from 1 to 2, this 1 to 2, it is compression happens here in the compressor, and 2 to 3, this 2 to 3, this condenser here, and this 2 to 3 condensation process happens in this 2 to 3, and 3 to 4, that's the expansion valve. Here the expansion happens from 3 to 4. This is the simple TS diagram of our vapor compression refrigeration cycle. Now if you try to understand in pH diagram, I have kept this pH diagram as well. So 4, 1, 2, 3 like this: evaporator, compressor, condenser and expansion device. So this is for information only. Now the refrigeration cycle diagram, whatever we have discussed, it is at ideal case, but at actual it's not like the same. There will be some losses. So let's try to understand in our TS diagram. This is the pressure line, here is the pressure line. So this process will be 1 to 3, like similar, but here will be some losses. 3 to 4, there will be some losses. 4 to 5, from 5 to 6 compressor, again some losses. 6 to 7, 7 to 8 some losses, and then again 11 to 1. So there are many losses will be there. So we will try to understand all the losses in our diagram for better understanding. So this is basically imply the actual vapor compression refrigeration cycle. If you see our diagram, you see this 1, 2, 3, the portion 1, 2, 3, that's this portion 1, 2, 3 indicates the flow of the refrigerant in the evaporator at suction pressure and temperature. This is the normal process. Then 3 to 4, this 3 to 4 is the losses. This portion indicates a pressure drop as there is a resistance of the suction valve to the compressor. Due to this resistance of the suction valve, there will be some pressure drop or losses. Now 4 to 5, 4 to 5 means this portion of the refrigeration cycle indicates the heat addition from the cylinder wall to the refrigerant. The cylinder wall will add some heat and it will end up with some losses. And then 5 to 6, this 5 to 6, it is the basic process, the compression process by the compressor. And 6 to 7, this 6 to 7, the small portions indicates cooling of the refrigerant at the outlet of the compressor. Yes, some full that's high temperature and high pressure, but there will be some cooling also at the compressor outlet because of the losses. And then 7 to 8, this 7 to 8, Here, this part of the refrigeration cycle indicates a pressure drop due to discharge valve resistance. So all the valves, pipe, everything will give resistance, and this is the resistance for the discharge valve, and this is the loss. Now, 8, 9, 10, 11. So 8, 9, 10, and 11. This part, refrigerant is desuperated to dry state. The latent heat is removed from the subcooling of the refrigerant happens. It's a normal process which we discussed already. Now 11 to 1. This portion indicates the throttling, that's the expansion process. So applications, different types of air conditioning machines, district cooling system, cold storage, heat pump, and many more. So you see, this is basically a chiller, air cooled chiller. Just we all know, but just for information, I keep it. So refrigeration cycle will be part of this. The package air conditioners, here also the basic route is the refrigeration cycle. Split air conditioner we have already discussed. So we can discuss if I have any questions. I think today we can sum up.